Okay, we will get started. If we jump straight in, obviously today we're covering CCD and CMOS sensors and the key comparisons between the two, or certainly from our perspective as a camera manufacturer anyway. Today we've got myself as the host of the webinar, and I'll be running through the vast majority of the content. I'm the Sales and Marketing Director for Attic Cameras. I've been with the company for just over a year now, and head up all activities, sales and marketing wise, and certainly working very closely with all of our customers as well. In addition, on the line, we have Andrew Kirby. Andrew is the white paper author, so hopefully you received your copy of the white paper in advance, probably with a few less scribbles on than my copy. And Andrew comes with a long background in physics, but also in scientific research spanning a couple of different decades. I won't mention which ones, and has been here with Attic for a number of years as well, covering a variety of roles from technical support, camera building, and customer support as well. In terms of the webinar itself, I'll just quickly pop through the structure of what we're going to cover today. Obviously, I'll be aiming to keep everything down to sort of 20-25 minutes with a bit of time for some questions at the end, just to make sure that we can cover off any other topics or areas that you're particularly interested in at the moment. As you can see on the screen at the moment, we will have a brief introduction. We'll run through some of the history of the sensor technologies, moving on into the architecture, or certainly from a basic principle. And then we'll look at a couple of those different comparative areas like binning, fill factor, shutter types, noise and QE, before following up with a quick summary and the Q&A, which we mentioned as well. In terms of an introduction, we know the debate continues about which sensor technology is the best. So we'll aim to cover some of those aspects involved in understanding the pros and cons. And certainly as a camera company, we utilize both technologies quite heavily. And we know that the answer isn't always as straightforward as one would hope. Instead, it's more often than not a combination of factors based on requirements, performance, and the future of each technology as well. And I know that might be a question that pops up as we go through. So with that in mind, let's move straight on. From a historical perspective, the initial developments came out of Bell Laboratories. So Boyle and Smith, in this instance, in the late 60s, they were looking for methods of transferring charge along capacitive devices. So it's all well and good being able to turn photons into a charge, but then what do you actually do with it? How do you do something useful? And in this case, obviously create an image. Simply put, the charge went in at one end and it could be moved along the line to the opposite end at a speed that could be easily regulated. So that allowed great control over those charges, and certainly when those photons were converted, something more useful could be done with them. Further development of shift registers, which we'll probably touch on the architecture side of things, then allowed for those movements around a sensor, which again we'll look at in more detail shortly. CMOS development wasn't that far behind, well, certainly not initially anyway. Its progress kicked off in the 70s, but it wasn't until the 90s really that commercial products became more readily available. Its proliferation at that point was then quite rapid. Obviously, becoming available in the 90s, and then by 2007 it had overtaken CCD as the volume sensor of choice, so finding its way into the mass consumed products. And as you'll no doubt know, it now features in most mass produced imaging technologies. You know, every mobile phone, every camera that you see dotted around, those on your cars, more often than not these days, are going to be featuring CMOS technologies. In terms of architecture, so, well, in this example that we're looking at on the screen at the moment, we are looking at an interline CCD sensor, though we do obviously have to note that other formats such as frame transfer or full frame also exist. The broad concept of their operation is quite similar, but if you want more information about those other sensor or other CCD sensor technologies, please do let us know and we can organize something separately. So in this instance, looking at an interline CCD, you can see, or hopefully you'll be able to see my laser pointer on the screen, the joys of modern technology, as we flow through the process of capturing an image, or certainly from a very basic perspective anyway. So at the beginning, we are looking for photons to arrive and to hit the photosensitive area on a CCD, at which point it is converted into a charge through the photoelectric effect, and it sits there in that pixel, ready to be read off or converted into some more useful information. So at the end of that image exposure, the transfer gate will then open up and move it into those shift registers that we talked about earlier. So first up, it'll go down the vertical register, and this happens very much in a step-by-step phase. So it uses a clocking signal to encourage these charges to move down. In essence, it's a positive minus or a positive negative charge that is moving that electron further and further down the ladder step by step. That happens for each pixel. They all get shifted in and they all get moved down one by one. And they then reach the horizontal register, where they then shift across through to the charge to voltage conversion, the amplifiers, and the output. So it can go through that analog to digital conversion process. It's at that point that obviously it becomes a digital process or a digital signal. Before then, this is very much an analog process. So as we can see with CCD, it is comparatively an analog technology until it gets that final readout stage where it becomes something more digital and is something we're able to utilize more heavily these days. In comparison, looking at a CMOS, well, just from the image alone on screen, we can see the architecture is very, very different. We can see that it utilizes a number of the core principles found in CCDs, but with some very key differences. Namely, that each pixel is doing the charge to voltage conversion at the pixel level. So it's doing it in situ rather than having to shift it all the way along all of those registers and all the way to that final stage. It's doing that initial process at the pixel level. As a result, it gives the CMOS sensor greater flexibility in terms of how it's reading out and in which format. So converting that process a little bit earlier on just gives the CMOS that additional flexibility and allows people to do different things much faster. Now, the drive for CMOS development really came as a result of a few different things. For one, it was becoming harder to reduce the cost further of CCD designs, or more notably anyway. Also, broader semiconductor manufacturing processes were developing at quite a high rate. CMOS was able to some extent, ride on the coattails of broader semiconductor manufacturing. If you're familiar with Moore's law, where the number of transistors on a chip should double every 2 years, then this continued realization will enable CMOS sensors to utilize these modern techniques for manufacture, which will help to continue driving performance forwards. In essence, as everything gets smaller, CMOS can potentially get more powerful or more capable. An example of this can certainly be seen with ever higher resolution CMOS sensors, though sometimes at the expense of pixel size. So moving on to sort of a performance characteristic in this instance, or a capability. Binning is probably a term that you might come across quite regularly, but not necessarily understand the impact of using one technology versus the other. Certainly, binning is heavily utilized in a wide variety of applications, notably those needing detection of lower light levels. It's also an area where the two sensors differ quite greatly. So you'll find a good numerical example in the white paper, but we'll try and give it a little bit of color here as well. So when imaging, a key parameter is often going to be the signal to noise ratio. In essence, do you have more signal than you have noise generated in your system? If not, you'd struggle to differentiate between the two sources and you won't get a particularly useful image, or certainly you'll get something which, you can't really tell what's on the image particularly. In general, you're going to want a signal to noise ratio in excess of 2.73 to start getting some more meaningful pictures. Now with the CCD, the sensor itself completes the activity on the chip. So if we were to look at the picture we've got on screen at the moment, it's taking, let's say, 4 pixels and combining them into one super pixel. Now, this happens on a CCD on the chip. As a result, it means you only get one hit of read noise when you're converting those combined charges. As a result, you can improve the signal to noise ratio quite dramatically. So in the example of this picture, your improvement would be fourfold. So depending on the noise in the system, this can be a significant improvement, which helps you to pick out the details in low light or quite faint images. For CMOS, however, if we think back to the previous slide and remember where those conversions are undertaken, you'll soon remember that they're at the pixel level, and as such, the read noise for each pixel is also combined alongside the signal. So whilst you can still get an improvement in the signal to noise ratio, it's going to be less impactful than that found with a CCD. And the example shown, it would double the signal to noise ratio, or certainly the example in the white paper. So at a low level, it's what feels like a fairly small gap between CCD and CMOS. But as soon as you start to increase that level of binning, that gap increases quite dramatically as well. So it's something that helps CCD to stand above CMOS, or certainly still to this date, from a binning perspective, and the applications where that is quite important. So it can be a useful tool for low light, but it can also be a useful tool for just increasing image download times, or certainly alongside subframing, for example. And for many of our customers, and certainly those trying to capture those low light images, binning is one of the biggest factors for the continued uptake of CCD-based cameras. So shimmying forwards, fill factor. Now, the name can be slightly misleading. We'll come on to sort of pixel fill or well depth in a minute. But when thinking about image sensors, or certainly when looking at this sensor here, it would be easy to think with the naked eye that the whole surface is suitable for capturing light and converting it into an image. But unfortunately, this isn't the case. If we think again back to those architecture slides, we might remember the pathways that the electrons and voltages need to travel along to reach the output. These wires and other associated circuitry can actually occlude some of the photosensitive area, and this will then reduce its ability to convert photons into electrons. Now, due to the integrated circuitry and on-pixel digitization, standard CMOS sensors can suffer more than their CCD counterparts when it comes to fill factor. But we'll have a look at some imagery to help further explain it as well. So if we look on the top left at this first image, we can see, let's say, a basic CMOS sensor from a design perspective, or from an image perspective anyway. At the bottom, we can see the substrate. So this is the supporting structure, let's say, for the CMOS sensor. On top of that, we've then got a photosensitive layer, which is where the photons are converted into electrons. On top of that, we've then got some of that componentry required to move those charges and voltages around, built into a supplementary layer. Now, in this example, we can see a couple of the photons are being blocked by the wiring, and as a result, the effectiveness of that sensor is going to be reduced where those photons are being blocked. Obviously, when it comes to imaging, we want all of that light hitting our sensor to be converted, but that isn't the case necessarily in in any technologies really, but certainly less so in these as well. If we move on to the right-hand image, we can see the addition of micro lenses. These are available for both CCD and CMOS sensors, and as the name suggests, these are minuscule optics that help to focus the incoming light. I almost think of them sometimes as sort of small contact lenses, helping to shape and focus and make sure the light is going to the right place. Again, as demonstrated by the image, it's bringing it in, helping it to avoid any of those occluding factors to make sure as much light as possible reaches that key photosensitive area. These are utilized in a large proportion of modern CCD and CMOS sensors, and certainly in many of the cameras we produce. And then if we bring up, when it loads up, there we go, the image showing backside illumination. Now, if we look at this, what might quickly become apparent is it almost looks like a flipped over version of the original image we have on the top left. Now, backside illumination is very much as it sounds. You're using the back side of the sensor and allowing light to pass through there. So this is to help alleviate the impact of components blocking light, and it's a newer technique that has been heavily utilized in recent years for both CCD and CMOS. So it takes that same sensor design, flips it over, and then that thick substrate layer, which used to sit above the photosensitive area, or below in this instance, is then etched away and thinned down to allow for better access to those photosensitive areas. So in its own right, that change alone will greatly improve the opportunity for light to reach its target. And then even more so when you're adding micro lenses as well to help focus that light in. So fortunately, backside illumination is more and more readily available, and it's certainly a technology that we at Attic and QSI are going to be utilizing in some of our new products due for launch in the coming months. In addition to the above techniques, improvements like improvements rather to lithographic techniques mean that all of these complementary components that are found on CMOS sensors will be taking up less and less space as the years go by. So if we again think back to Moore's law, we'll know that these changes will help to reduce their impact, and even for front side illuminated products, it may have less of an impact. Certainly backside will have a much better impact. But again, that's something which will only improve those technologies as the years go by. Whilst we've got these images on screen as well, it's worth going back a bit onto the fill factor sort of name and talking about full well depth. Now, full well depth refers to how many electrons a pixel can hold before filling up or overflowing, let's say. If we view each of these pixels, so the photosensitive area as a bucket, it can only contain a certain amount of electrons before it would start to overflow. This overflowing, let's say, can cause a number of different artifacts on an image, be that blooming, where it spills out into other pixels, or you might have smears or streaks where you get a bright line coming down your image. So it's important to understand the impact of full well depth, especially depending on what type of imaging you're doing. If you've got certain areas which are likely to be quite bright, then they might fill up those wells a bit faster. As a result, if you want to be able to have definition between much brighter and much darker areas on your image, you might want to have quite a large well depth to capture both of those during an image. So it's not necessarily important to all customers. Certainly if you're doing shorter exposures or doing things on really, really low light levels, modest well depths might be of more interest. Certainly we try to provide a variety or a wide variety of well depths to our customers. Some more modest well depths at say 10,000 electrons, going up to the high tens of thousands potentially on our newest products, reaching the hundreds of thousands. And certainly that's on our upcoming E2V based camera system, which is yet to be announced actually, so my marketing team might tell me off for that one. Also, whilst we're looking at these images, we want to quickly note dynamic range. And certainly whilst having just noted full well depth. So full well depth impacts or can impact dynamic range depending on how it's calculated. And the dynamic range in essence is the value, or helps to indicate how many different shades of, well, for a mono sensor, how many different shades of gray a sensor can represent. In theory, the higher the value, the better the ability to distinguish variances from pixel to pixel. So if you've got an image with a lot of variance, a higher dynamic range is going to help you pick out those details, certainly in those faint images. Most of our cameras certainly operate in either 12-bit or 16-bit modes, which gives you, let's say, 4,000 shades or 65,000 shades for a 16-bit image. Okay, onto shutter types. Now, shutter technology is, again, another notable area where the sensor types can differ greatly. Historically, for CCD sensors, they'll use either an electronic or a mechanical shutter. In the instance of an interline sensor on the top left here with our Attic 460, This uses an electronic shutter. Simply put, it's controlled via the software, and each pixel can effectively start or stop simultaneously. So it will take a full image using the whole sensor, and then it'll stop the exposure, and it'll transfer those charges through. Mechanical shutters are more likely to be used with full frame sensors. In this instance, as seen with our QSI 683. In this example, as you'd expect, a physical shutter will rotate and occlude the sensor to prevent any additional light hitting the imaging surface. This is a result of the sensor architecture, which, if it was continued, or if it had continued light hitting the surface during the readout phase, it could create strange artifacts or corrupt the image. So as a result, mechanical shutters are utilized for that particular sensor format. In general, they'll be fine for most applications, but as you can imagine, certainly when compared to an electronic option, they are likely to be a bit slower in nature. So they might not fare quite as well in very short exposures where the shutter can't physically move quick enough, and as a result, you'd have some sort of artifact of that shutter rotation coming over your image. Now with CMOS, it's a little bit more complex. Whilst able to use a mechanical shutter if desired, certainly, they tend to utilize two options in their own right, sort of built in. The first is rolling shutter, as we can see on the screen. In this case, an image is captured and read out in sections, row by row, for example. Each section is then added together to create a full image as though it were taken at exactly the same instant. However, for faster movements, it can cause images to be distorted or unbalanced. So if ever you think of someone who's taken a picture on their phone of a helicopter and it might look like the blades are twisted, that's a result of that rolling shutter. For static, slower moving, or subjects with, say, low brightness variance over time, this isn't a problem. It's just going to be more likely in those faster environments where a rolling shutter will fall down. The other option that we can see on screen is the global shutter. So this is another term that is quite common and you'll have probably heard of already. And as the name suggests, it allows for the whole sensor to capture an image simultaneously. So it removes that likelihood of that blurring effect seen in a rolling shutter. It does, however, require additional circuitry to achieve that, which again, going back, can impact the fill factor and the performance of the camera. So something to bear in mind that, again, you might get one benefit, but then it'll fall down in another aspect instead. So both formats, CCD and CMOS, have their pros and cons and different capabilities when it comes to the shutter types. And again, it starts to come back to what do you need to help inform which way you go on that route. Noise. So as we touched on earlier with the signal to noise ratio, noise, or sort of uncertainty, let's say, is another area where the two technologies perform differently, or certainly can do. Now, the two main types of noise we look at on this slide are read noise and thermal noise, or dark current as it's often referred to. Now with read noise, as you'd anticipate, or certainly if you're familiar with electronics, the process of reading an image inevitably creates a level of noise. So that conversion from charge to electron through to a digital format at the end will create noise as it goes through that process. Now with CCDs, fortunately, well, from a statistical perspective, that noise is created in a fairly normal distribution. So it makes it easier to calculate and then give a more, let's say, exact value. And in most CCD sensors that you'll see on the market, that's kept down below 6. You'll see sort of 2, 3, 4, 5 as a value there for the read noise levels on those cameras. Now, in the case of modern CMOS sensors, read noise levels can be very low, but the complex circuitry will often lead to greater variation from pixel to pixel. So as a result, if we thought CCD as a nice normal statistical distribution, CMOS can be a lot more scattered, which makes it a lot harder to give a precise value due to that heavily skewed distribution. Thermal noise however, is something that certainly impacts both sensor technologies and, as the name would indicate, refers to the process by which electrons are thermally excited and released from the silicon into the sensor. So the size and rate of is related to their rate of release, hence it's measured in electrons per pixel per second. And it can be a very significant contributor to the signal to noise ratio, especially sort of at ambient temperatures. Cooling in that sense then becomes a very important aspect and capability of a camera, certainly for anything which isn't a very, very quick image. Now, with CCDs, this cooling can help to half the level of thermal noise for every 8 or so degrees that the sensor's cooled below ambient. For quite a lot of common sensors, like the Sony ICX range, this is very, very effective up to about -10 degrees. If you view it as a sort of a curve, it's quite a rapid improvement down to about -10, at which point that improvement gets less and less. So a lot of people you'll find, and a lot of camera manufacturers, ourselves included, don't seek out to get that cooling much below sort of -10 as a real world figure. Because the benefits just aren't worth the additional cost and investment in trying to get that cooling further down. CMOS sensors do also benefit from the cooling, especially due to the large amount of circuitry around the photosensitive area. Amp glow is certainly a common term and a common sight in CMOS sensors, but again, with good cooling and good electronic design, it can help to mitigate that impact. But it is certainly something that's, especially due to the more complex nature of a CMOS sensor in terms of how it's mounted, makes it a harder device to cool in general. When it comes to noise, if you want some more information, we do have some great videos on our website where Steve Chambers, our MD, runs through those different noise types and goes into a bit more detail on each specific one. So by all means, check those out as well if it's a topic of interest. Spotting the time, I will dash on. This is our last main slide anyway. So quantum efficiency, or QE, as it's often referred to, is an important consideration, again, when selecting a sensor or camera. So it's usually expressed as a percentage, as you can see on the left-hand side of this graph. And it refers to the sensor's likelihood of converting photons into electrons, quite simply. As we sort of highlighted in the previous slides, a number of factors could impact this performance. So the scattering or occlusion of light will reduce that percentage. And whilst a percentage is often, or a single percentage value is often given, this will normally only refer to the peak performance on the QE graph. So one thing you should keep in mind when looking at various cameras from various manufacturers, if they just give you one reference value, a peak QE of 70%, let's say, it's always good to try and remember that that is just a peak at a very specific wavelength and not throughout the whole performance capability of that particular sensor. So we must instead be mindful of the fact that these sensors do have varying performance across the full spectrum. As we can see in the graph, it will change quite dramatically depending on the wavelength. So a lot of the sensors that will be readily available tend to operate quite effectively in the visible spectrum. But you will see a very rapid tail off in the UV and in towards the infrared ends of those spectrums. So it just highlights not only the importance of understanding what you want to achieve or what you're trying to detect, but certainly this graph anyway helps to highlight the variances from sensor to sensor as well. So just because you're utilizing one camera, that camera might be able to utilize a variety of sensors. So it's understanding which one of those might be the best option for your particular application. Historically, CCDs dramatically outperformed CMOS for QE, but in recent years, CMOS has absolutely greatly improved and can now exhibit much, much higher QE levels than previously managed, certainly with the newer back-thinned variants as well. So one final thing to note, I suppose, on QE is that whilst in its basic form, let's say with these shown on screen now, a sensor might have a given set of performance characteristics, but with some clever manufacturing techniques and materials using deep depletion or performance coatings that can be applied. These will help the sensor to perform better in other wavelengths. So deep depleted sensors, for example, you'll start to get better performance towards the infrared. And you can get UV coatings, which will help to improve their performance down in the UV range as well. So this is something that's certainly available on sensors now, with manufacturers such as Teledyne E2V, who we're working with at the moment for future releases, are able to create this type of sensor, and fortunately make it something that we're able to react and reflect on depending on what our customers require. Okay, so spotting that we've just about used up our full allocation of the half an hour I tried to promise you earlier, we'll wrap up with a quick summary before a bit of Q&A. So as we've seen throughout this webinar, there are a number of performance characteristics that help to differentiate between CCD and CMOS. Each technology definitely has its strengths and certainly has its weaknesses. When selecting a camera for your needs, it is important to understand your requirements first and foremost, as that will help to guide that selection process to make sure you get the right camera for you. It's certainly a service that we at Attic and QSI are able to provide, and certainly where we find our strength is being able to not only help narrow down those requirements and find the perfect solution, but also to utilize our ability to create bespoke solutions that meet your precise needs, in essence. Before we finish up with a quick Q&A, just wanted to remind you that you can obviously get in touch with us anytime via our website or using the email address shown on screen. You can also subscribe to our newsletter or follow us on LinkedIn for all the latest news regarding future webinars, product releases, and the latest market trends. And we'll also send out a follow-up message after the webinar, which will include links to this video to watch again, to share with your colleagues. And I think it will also fire over a quick questionnaire at the end of the webinar. And it'd be great if you could provide some feedback and to let us know if there are any topics you would want covered in future as well. So let's have a quick look and see if we've got any questions from the floor. Oh, it certainly does. Right. Scrolling back through. Okay, does the binning process in the same Sony CMOS IMX model sensor always performed in the same way, or depending on the camera manufacturer implementation? In other words, is a feature associated with the CMOS chipset from Sony, or depending on the manufacturer? So I'll jump in and then Andrew can correct me. Okay. In essence, the binning is always done off chip. So it doesn't make a difference who's made the camera. In this instance, the binning will be the same for that sensor. So the only things that might change are how the manufacturer has designed the electronics and how that impacts on the noise levels within the camera. So your read noise, your thermal noise. So those elements can certainly impact your signal to noise ratio, but the actual binning itself, in essence, is done in the software. So it's just combining those 4 pixels and the data from it into one. So that bit will be remaining. It's just then how the camera design impacts that more front up. Okay. Glad Andrew agrees, so that's okay. Yep. In forums, I have found that the binning of some cameras or manufacturers are performed in the SW part of the camera, but after this webinar, always done in the same way for the main chipset. So yeah, so going back again, that's very much saying, yeah, for CMOS, it's going to be done in the software, so it's done off the chip, but for CCD, it is very much done on chip. Equally, it could be done in the software, but whilst you've got that benefit of being able to do it on the chip, absolutely, that's what we would recommend, and that's how we do it ourselves. Certainly, we've got the capability to force bin cameras if people want those super pixels, let's say, permanently, or abnormally shaped pixels. They're looking to do rows. It might be for spectroscopy, things like that. So there are lots of different options available to you. Okay. Right. The last question I think I've got here, obviously. Double check through. Some sensors with a color version and a mono version, usually the mono the same, the color without the beta filter, but I've read about the need to remove micro lenses. over the sensor in those mono versions because of the Bayer filter is built in the surface. It happened the thing with the medium aperture. So, Andrew, do you want to jump in on that one? As I was saying, I'm still reading. I think you're probably ahead of me.
Yeah, unfortunately, the text is quite small in our little chat room there. But essentially, none of the sensors that we use has filters from the lenses, micro lenses removed. So the only differences you will find is monos have the Bayer filter matrix, and sorry, the color has the Bayer filter matrix, and the mono ones don't. So if you had a situation where you had a mono sensor with or without micro lenses, you'd have a very big difference in efficiency between the color and mono chips. And that's not something we use. All of our sensors have micro lenses.
Lovely stuff. Thank you, Andrew. It looks like we've got one or two other quick ones which we haven't published yet. So, what are the key characteristics of an application that would determine whether CCD or CMOS is better? I suppose we've covered that to an extent through the course of the presentation, but from an application perspective, things like speed, light levels, and the optics will play a big role. So if you need high frame rates, for example, you're looking for something which is a bit more live, let's say, then CMOS is more likely to suit your needs. But if you're imaging in low light levels, in fluorescence applications, for example, especially where you're looking to bin, then CCD continues to shine. No pun intended, apologies. Next question up, CMOS seems to be evolving rapidly. Is it likely it will be a better option than CCD for the majority of applications in the near future? So it's certainly evolved rapidly over the last decade or two, and I don't expect that to change anytime soon. However, these developments are more heavily driven by industrial and consumer markets. As such, they're going to evolve, but not always in a direction that's suited for every application. So sensor technology that finds its way into your phone or a line scan camera in manufacturing, for example, is unlikely to have the performance characteristics needed in scientific imaging, for example. So whilst there may absolutely be benefits, they might not always be things that we would want to utilize or our customers would want to utilize. The final question I think I've got here, what is the future of CCD? Is anyone really making them anymore? Well, to the point. In short, yes. We're currently working with Teledyne e2v to incorporate some of their sensors into some of our new cameras. So whilst Sony and onsemi have stopped producing CCDs, albeit you're still able to buy them through heavy stocking, e2v have actually committed to the long-term support of the technology. So CCD isn't going anywhere. It will evolve, it will change, new products will come out, certainly not at the rate that CMOS will be doing, but in the example of e2v, they are committed for several years, if not decades, on space missions and other such projects that they're working on with bigger organizations like ESA, NASA, Chinese Space Agency. So they will be ensuring that those technologies are supported for the long term. And certainly they have invested heavily in making sure that that's the case as well. We do actually have a quick extra question or two. I'll try not to keep you much longer. So, will dynamic range of CMOS increase soon from 12-bit to 15-bit? Well, there's actually CMOS sensors coming out which are 16-bit. And true 16-bit as well. So there are sensors which, if not available now, will be available soon at 16-bit. Certainly there are a number where you might have a 16-bit conversion, but the sensor does still run at 8 or 12 and just utilizes that wider conversion capability. I don't know if you had anything else to add on that one, Andrew?
Yeah, the dynamic range is actually the space between your floor, your noise floor, and the full well capacity. So changing the electronics to a greater bit depth is not just going to intrinsically increase the dynamic range. It's just going to allow you more precision when it comes to distinguishing those grey levels.
Super stuff, thank you. And we do have one more in at the end there. So I've heard that CCD manufacturing is being greatly curtailed. So absolutely, as I just covered, yes. In short, you are right. The two of the biggest manufacturers in Sony and onsemi are no longer making CCDs. Thankfully, we do have access to good stocks. So we will be certainly the Sony cameras we're making. The bigger running lines that we utilize, we are expecting to still be able to make cameras using those sensors for the next 5-6 years as a minimum. But it wouldn't surprise me if we go beyond 2026 with the kind of stock levels that were built up. And again, to reiterate, people like Teledyne E2V, although in the minority now, are committed to making CCD sensors for the long-term future. And that's one of the reasons we're looking to incorporate those sensors into our future cameras as well. Lovely stuff. I don't think I can see any more questions or any that we've missed at the moment. So if that's the case, I will firstly apologize for running over by a good 10 minutes with these extra questions. Hopefully we've helped to cover those off for you. If you do have any other questions that pop up after the webinar, please do get in contact with us, let us know, and we'll do our best to help out. I fully expect that we'll be running some more webinars in the coming months as well. Mentioning E2V, I'm asking some former colleagues from E2V very nicely if they'll happily join us on a webinar to talk about the future of imaging technologies. So hold that space. I will let everybody know as soon as we've got anything booked in. And obviously, if you've got any ideas or suggestions for future webinars on topics that you'd like us to cover, again, please do let us know and we'll do our best to cover those. Other than that, I will say thank you once again for joining us. I know we've got people scattered around the world in the US, in Japan, in Europe, all over. So it's much appreciated that you've taken the time out. Please do feel free to send this on to your colleagues afterwards as well. And we'll hopefully speak to you soon. Thank you very much.